Sun, we have arrived. This star is extremely hot. Let's reveal the facts about the sun and subscribe. 11th, going to peel back its layers, understand its explosive temper, and even peek into its distant future to see how its story, and ours, will eventually end. This isn't just a list of facts, it's the biography of our home star. So buckle up, because we're about to go on a journey 93 million miles away to get up close and personal with the most important object in our sky. We'll see how it's basically a giant nuclear fusion reactor, why its atmosphere is bizarrely hotter than its surface, and how its invisible winds create a protective bubble around our entire solar system. These aren't just trivia points. Understanding the sun is key to understanding our place in the universe. In this video, we'll explore 12 essential facts about the sun you must know. 10th, let's talk ingredients. If you were to build a star like our sun, what would you need? You might think it's a complex recipe, but it's surprisingly simple. The sun is overwhelmingly made of the two lightest and most abundant elements in the universe: hydrogen, helium. Think of it like a cosmic cloud that got so big it collapsed under its own weight. About 74% of the sun's mass is hydrogen. This isn't just any hydrogen. It's the fuel that makes the sun shine. The second ingredient is helium, about 24% of the sun. Most of this helium wasn't there at birth. It's the byproduct, the ash, from nuclear reactions in the core. So the sun constantly turns hydrogen into helium, which means it has a finite fuel tank. The other 2%? Oxygen, carbon, neon, iron, trace impurities to the sun, but crucial for us. It shows our sun is a second-generation star formed from recycled material, enabling rocky planets, and us. 9th, we all know the sun is big, but our brains have a hard time grasping the sheer scale. Saying it's big is like calling the Pacific Ocean a bit wet. Line up Earth side by side and you'd need 109 to span the sun. In volume, you could fit about 1.3 million Earths inside it. Every city, every mountain, every ocean, multiplied by 1.3 million to fill the sun. At 600 MAF, 3 weeks around Earth, over 6 months to lap the sun, non-stop. It's so big that different parts rotate at different speeds, a phenomenon called differential rotation. It's not just another object, it's a realm so vast our planet is a humble visitor. Understanding this scale is step 1 to grasping its power. Eighth size is only half the story. The other half is mass, where the sun really throws its weight around. It accounts for 99.86% of all the mass in the solar system. Everything else, planets, asteroids, comets, the leftover 0.1%, a cosmic rounding error. This mass gives the sun immense gravity, the invisible hand that sculpted and sustains our solar system. Without it, there'd be no stable orbits, just rogue worlds wandering the dark. Its pull sets our year and corrals belts and distant comet reservoirs. We see its light and feel its heat, but gravity is its most profound influence, the master puppeteer of a celestial dance. 7th, so the sun is huge, massive, hot. But what is actually powering this thing? The answer isn't fire. You can't burn in the vacuum of space. The secret lies in the core, nuclear fusion. The same process as a hydrogen bomb, sustained steady for 4.6 billion years. 15 million degrees C and 250 billion atmospheres bend the rules of matter. Hydrogen nuclei are forced to fuse through the proton-proton chain. 4 protons become 1 helium nucleus with a tiny mass loss. That missing mass becomes energy, E equals mc squared. Roughly 600 million tons of hydrogen become 596 million tons of helium per second, when 4 million tons become pure energy. Gamma rays and neutrinos power the sun, producing the light and heat we receive. Not just hot gas, a celestial engine forging new elements and setting its fate. Sixth fusion in the core. But how does that energy get to space? Layers. The core. The only place hot and dense enough for fusion. The engine room. Then the radiative zone. So dense, photons zigzag for over 100,000 years. Absorbed and re-emitted endlessly. Light warming your face today was born long before civilization. Next, the convective zone. Energy moves by convection. Hot plasma rises, cools, sinks. We see its tops as granulation. Finally, the photosphere, the visible surface. Above it, the thin, reddish chromosphere, and the wispy million-mile corona seen in eclipses. Core makes energy. Middle layers transport it. Atmosphere releases it. A star's blueprint that warms Earth across 93 million miles. Fifth here, a fact that breaks intuition and puzzled scientists for decades. From the 27 million degree core to 5,500 degree photosphere, it cools as expected. But then the atmosphere heats up again. The corona skyrockets to several million degrees. This is the coronal heating problem. Leading ideas. Magnetic waves channel energy upward. Countless tiny nanoflares collectively heat the corona, and magnetic reconnection snaps field lines, dumping energy. Photosphere is heated from below, but the corona from a vast, invisible magnetic web stretching into space. A stunning reminder, our star still holds deep mysteries. Fourth, look closely and you'll see dark patches, sunspots, not random blemishes, but magnetic indicators. They're cooler than nearby plasma. $7,000 degrees yields $10,000 degrees, so they look dark. Strong magnetic fields poke through, inhibiting convection, like a lid on boiling water. A single spot can match Earth's size. They appear in pairs or groups with opposite polarities. Loops arch through the corona, trapping superheated plasma and sculpting ultraviolet arches and streamers. Spot counts rise and fall. Many spots mean tangled energetic fields, solar maximum. Few or none, solar minimum. They're warning signs of stored magnetic energy primed to snap. Third, the rise and fall of sunspots follows an 11-year rhythm, the solar cycle. Quiet at solar minimum, peppered with spots at solar maximum, then back again. Spots emerge at mid-latitudes, increase over 5 to 6 years, and migrate toward the equator. Differential rotation stretches field lines like rubber bands until loops burst through, forming spot pairs. It's truly a 22-year magnetic cycle. After each 11-year sunspot cycle, the sun's magnetic polarity flips. North becomes south, south becomes north, needing 2 cycles to reset. Second, when tangled magnetic energy lets go, we get solar flares and coronal mass ejections, CMEs. A flare is an intense burst of radiation from sudden magnetic reconnection, like a rubber band snapping. It blasts energy across the spectrum. A large flare equals millions of H-bombs, reaching Earth in 8 minutes. CMEs are ejections of matter, billions of tons of magnetized plasma, racing at hundreds of thousands to millions of mph. A fast one can arrive in 24 hours. Think flares as the muzzle flash, CMEs the cannonball. Aimed at Earth, a CME slams our magnetic field and triggers a geomagnetic storm. Dramatic space weather. We're safe on the ground, but our tech isn't. Power grids, satellites, GPS, and astronauts face hazards. Prediction is critical. First, the sun constantly breathes a supersonic stream of charged particles, the solar wind. The corona is so hot gravity can't hold it. It expands outward, filling the solar system. The wind carries the sun's magnetic field into a giant spiral, the Parker spiral, like a spinning sprinkler. This outflow forms the heliosphere, the sun's sphere of influence, with its edge, the heliopause, where solar wind is halted. Voyager 1 and 2 crossed into interstellar space, confirming it. The heliosphere shields us from many galactic cosmic rays. It sculpts planetary magnetic fields and blows comet tails away from the sun, a dynamic boundary of our home. Let's quickly recap. So there you have it, secrets of our home star. From its mind-boggling scale, fusion-powered core, violent temper tantrums, to its ultimate fate. The sun is more than a light. It's a dynamic, complex anchor of our existence and a source of enduring mystery. Studying its cycles and outbursts teaches us how to protect our technology and way of life. Its life cycle mirrors countless stars, a key to our galaxy's past and future. Next time you feel the sun's warmth, remember, it's the end of a 100,000-year photon journey from a nuclear furnace 93 million miles away. We live in the glow of a magnificent star. What are your thoughts about the sun?